So, where can I start? So this is a shorter version of a talk that I gave at Pivotal Labs about 6-8 months ago. So if you've heard it before, I don't know if you were there, my apologies, you're going to hear it again. So I started at Livestream about 18 months ago, joining as the VP of Engineering to help manage the engineering teams in New York City. Before that, I was at Rtmp, and before that, I was actually at Pivotal Labs as sort of a tech for hire. So I was lured away by this opportunity to start running teams and to start diving into a sort of a different and new problem. I had been at Rtmp for I think over 5 years when I left. It does feel like quite a long tenure these days in sort of the tech world. But I have to say that I was pretty fearful at first because what I envisioned was this sort of massive unknown problem space that I didn't know anything about. I didn't know anything about video. There's an acronym soup out there of video codecs and protocols and qualities and terms, and it's dense and it can be really hard to work your way through. But thankfully, what I sort of realized, and I guess what's sort of the thesis of this whole talk, is that my prior experience with web services ended up being extremely applicable. That video today on the web, on the modern web, is largely driven by the same web technologies and can be solved by the same web problems that you're probably working on already. That a lot of those solutions are transferable, and that much of that fear can be dispelled. So we'll dive into that a little bit. So to start, if we back up, let me put this down. What's the Livestream platform? It's really simple. It's a whole bunch of services running in the cloud, and it takes in video from a bunch of encoders. So these are things that take video, compress it down as something that's manageable, ship it all up to the cloud, and then our secondary responsibility is to get that in front of people, so play it back. And so we can take that now and dive in a little bit more, and at the top of our entire architecture stack are our CDNs. Extremely important. When you're dealing with a ton of load, when you're dealing with highly cacheable content, you definitely are starting to rely really heavily on the players out there who can actually handle this. Today, for us, that's Akamai and Fastly. Underneath that, we have the layers that sort of support our playback mechanisms. So this is the website, the player itself. It's Flash and HTML5 today. You have the mobile SDKs and the playback SDKs as well. And then sort of next to that as a sister service, you actually have APIs. And these, for us, are developed with pretty common web technologies that we're all used to. We use Node.js and Scala, Java, sitting on top of common OSS stuff, RabbitMQ, Redis, MySQL, Postgres. And for us, we actually split all of our services across 3 data centers. We're using a colo up here on the west side of Manhattan. We're using Google Cloud Platform, and we're using AWS. And a lot of that's about redundancy, about ensuring that we're actually live and online all the time. Customers with us often just get one shot. You know, you hit the button, you want to go live, and if that fails, you're sort of done. Your opportunity to win that customer is sort of over. So we do a lot of work to provide redundancy, and it can be a bit of a headache, though. You can imagine that straddling these 3 sort of data centers means that you're relying on sort of the lowest common denominator, which is pretty much just like a VM if you think about it. But besides the point. So that said, you know, all of that sounds pretty familiar. I'm sure a lot of you have touched upon one or many of those things already. Video does have its own special challenges, and they are unique and they're pretty fun to deal with. For starters, video is voluminous. There's nothing out there quite like the sheer size of video. And as we've seen quality get better and better and better over the years, 1080p, 4K, 8K, I mean, there's all sorts of crazy new things coming down the pipe. These present problems for us because it takes up an enormous amount of disk space to store all this stuff. There's this sort of tendency that when you're in the cloud, especially if you're thinking like thumbnails or images or text, I'll just throw everything in S3, the cost is cheap, the cost is getting cheaper every year, it's no big deal. That is totally a falsity when it comes to the petabytes and petabytes of video that you have to deal with, because that cost really does matter. It gets heavy and you're paying it every month. On top of that, you have to deal with I/O. And when you're talking about gigabits and gigabits of I/O transiting over channels going from VM to VM, little stutters and blips actually matter, and they can kill you. In fact, my boss likes to tell this early story of how we were a customer of AWS's way back in the day when they were still beta, and they essentially kicked us out of the program because we were swamping their system with I/O, and they couldn't handle it, and we were affecting other customers. The other problem that we have is that a lot of the work we do is very CPU intensive. Serving web requests is obviously a pretty burdensome task, but now when you add the problem of transcoding, for example, from one quality to another, you're actually taking video, you're decoding it, you're doing something with those pixels, and then you're re-encoding it, and that essentially locks up an entire core during that process. And when you take video and you're transcoding it into, for example, multiple qualities, you've now easily consumed the many cores available to you on a box. So if you want to do this en masse, you need lots and lots and lots of CPUs. So you're provisioning lots and lots and lots of servers, and that obviously gets really expensive. So, and then finally with live video, you do have this sort of special consideration to latency. You want your customers to be on that bleeding edge of live as much as possible. And that's hard to do. And I'll show you more examples of sort of how we approach that and how we tackle it. So, however, again, back to the thesis, I will contend that many of these problems are web problems and that we can solve them with web technology and with web solutions. And let's talk about the first problem. And it's one that I think bites a lot of us, and that's how to deal with long-lived connections. So if you think about video, especially back in the day, video was transited from server to client as essentially just like a stream of bytes. That's it. You essentially opened a connection, said give me the video, and it would just start flying over the wire, hopefully as fast as possible so that you could keep up. The problem there is that you essentially have this giant persistent connection, and now you're opening one for every single client who wants to watch your video. And why is that expensive? Well, eventually your server is going to catch on fire because it isn't able to necessarily, you can't cache this content. Everyone needs their own unique stream starting at a certain point. There's maybe state that's associated with that connection. And there's a lot of corollaries and sort of other web technologies out there. If you've dealt with web sockets, if you've dealt with large media uploads or long polling, then you know that eventually you can only pack so many connections on a given box before you need to start to horizontally scale this service. So it's a common problem. But with video, it's compounded by the fact that, well, you need it to be timely, and it can't stop. You can't really interrupt it. So the solution that the industry as a whole came up with, and I'm going to speak here to a broader solution, is the same one that we find in computer science and technology over and over again. We take a continuous process and we chop it up into discrete, manageable chunks. And the solution that the industry sort of revolves around today, and it's not the only one, but it's something called HLS. Excuse me for a sec. So HLS stands for HTTP live streaming. It was invented by Apple, and the idea is let's take this video and let's carve it into a ton of tiny little pieces, and then let's fetch them all with just HTTP. So no more custom TCP connection with a weird protocol between two, client and server. Now it's just straight up HTTP. And that means that essentially what you needed to download and keep a long connection open before, you can now just grab the little pieces as you need them. Why did Apple invent this? Well, when they came up with the iPhone, they realized that a mobile phone and a persistent TCP connection are two things that don't mix very well. You can imagine that walking around and connecting from tower to tower or ducking into the subway, your connection's obliterated all the time. So they needed to come up with a way to still deliver video to phones reliably. So they invented, it's fair to say they invented HLS, although there are other competing protocols that operate in a very similar manner. But this is definitely the most popular one today. So here's an example. This is your network inspector in Chrome, and this is just pulling down a straight up MP4 file. So this is the traditional way that we would serve video to a client, and it's just this never-ending, growing data feed coming in through one connection. And you can see that, there it goes. HLS offers us a different sort of topology. Now what happens is that many tiny requests start to bottle up one after the other, after the other, after the other, and this gives us all sorts of new capabilities and advantages. It may not seem optimal, from this point of view, but what do we gain? So it's just HTTP, right? It's the same protocol that we use for text, for JSON, for images at this point. And that means that there's a whole raft of technology out there that knows how to speak to this already. We don't need to cook up anything new. There's CDNs, reverse proxies, caches that can speak this language. They don't care what's inside, and they'll just work with it. So now immediately we've gained the benefit of being able to use all these common tools that we were all used to, and it helps us deliver video, which is pretty amazing. Let's unpack it just a little bit to give you a little window. What is HLS? It's just a playlist. That's essentially it. It's a playlist and little chunks of video. And that playlist is actually built on an old standard called M3U that Apple pioneered. That was basically, you look at it, it's just like a list of URLs, and that's it, nothing more. There's a master manifest generally that we call the index manifest or the master manifest, and that will contain several variants. These are the different qualities or sub-indexes. So if you look at the M3U8 file, you peer into it, it'll return to you several other URLs. If you open those up, then you'll actually get URLs that point to your actual video segments. And those are the ones that you're then essentially going to pull down in order. So your job as a video player is just to grab this thing, parse it, it's just a text file, and then start playing the video. And there's obviously a lot of specification around how you play it, when you rebuffer, how many segments to keep in your buffer, et cetera, et cetera. It's not, however, completely foolproof. Especially with live video, there are certain challenges associated with HLS. So, as I've mentioned, the video itself is segmented into little pieces. And when those pieces are requested, and those pieces are generally of a certain duration. So within the industry, we'll talk about 10-second chunks or 6-second chunks or 5-second chunks. And in some cases then, that adds an artificial delay onto the video without you being able to really do anything about it. The HLS specification, I actually read it after I drew this, but mandates that you have to keep 3 chunks in your buffer before you start playback. So if you have 5-second chunks and you are building a player according to spec, you have a 15-second delay that's just built into your stream without you doing anything else. And now once you add all the other sort of pipeline steps that happen when getting your video online, you've created even more of a delay. And part of our job as being in charge of live stream is trying to shorten that as much as possible. Other things that can happen are that as you decrease the size of the segment, let's say you're trying to get to like a sub 10-second delay. So hey, I'll beat the system by creating 2-second chunks. No big deal. Well, now your playlist is longer. You've got a lot more chunks to deliver to clients, and that M3U8 keeps getting updated with new segments, every time new content comes online. So if you're a player, you're requesting this M3U8 over and over and over again, and as the chunks get smaller, you have to request it more often. So you start to see a lot of churn. And HTTP doesn't come without some overhead, as we know. There's headers, there's compression, there's all the sorts of other stuff that happens. So it isn't a perfect solution. There are alternatives that we and other companies in the video space are investigating. One is known as Mpeg Dash. This is a cross-industry group, pioneered this one. It has sort of an alternative to HLS. It provides a way to create a template so that rather than having to read the manifest over and over again, it just tells you, like, this is what the URLs will look like. Just go ahead and follow that template and just keep requesting segments. So you've at least cut out that half of the cycle. You don't have to request the manifest over and over again. And then another mechanism for delivering video is just Rtmp. And this is your classic persistent TCP connection between client and server, and just send me all the video over Rtp, which is an older video protocol. Facebook is actually using this because it's extremely low latency. I mean, essentially you can deliver video from source to destination with just maybe tens or hundreds of milliseconds of delay by the fact that Rtmp encodes things in extremely tiny slices. So we'll talk about another problem in the video space now. And if you have any questions later, obviously let me know. The problem of authorization is tricky in the video space because essentially what we want to do is we want to broadcast video to all of the people out there that want to watch it, but we do want to make sure that you're not an unauthorized person who may be sidetracking and grabbing our stream and rebroadcasting it elsewhere. the classic use case and the classic problem that we have is that people will, well, you know, you might grab a screen grab and broadcast like a soccer game, like a UEFA Champions League match. And then a whole bunch of people will go online, and instead of going through our API, we'll just sort of point to the actual video itself and start grabbing the segments and then watching it through like an alternative player. That's something we want to avoid because we're paying for all of that bandwidth. You know, it's not free, it's still video, it's still transiting over someone's internet, and the bill falls on us. So this isn't DRM, for example. We're not we're not locking the video with a key that then requires you to unlock it. What we simply want to do is just ensure that you came through us to get the video. How would we do this if we mentally model it? Well, if there's a server and it's delivering the video, we want to authorize it, and we can do that by signing a key or having a database that's saving some state about every request, every visitor that's coming to us. But how do we do that with a cache in front of us, right? So, you know, there's an M3U8, it's just a text file. There's segments, they're highly cacheable little HTTP segments. We definitely want as much of that as possible to be absorbed by the CDN at the edges, not absorbed by us on the back. But if we throw a cache in front, and we still want to authorize all the requests, but they're no longer terminating at us, how do we solve that problem? Well, the answer sort of lies in a pretty simple mechanism that you see used over and over again, and again, is sort of borrowed from web services, and that's to move authentication to the cache layer. And this is actually well supported now by a lot of CDNs through a mechanism called tokenization, or through a lot of other web proxies out there. In our case, we use Varnish. And Varnish provides a lot of ways. I mean, if you've looked at VCL, I'm pretty sure it's Turing complete. You can do almost anything in their configuration language. So what we do, when a playlist is requested from us, we have a key on the server, and we add a little token onto the end of the playlist URL that we return. And then when that playlist is actually requested, Varnish accepts it. Varnish has this knowledge of the same private key. Now this is mandatory, like there's no other way around this, but we need to share some secret across both services. That's a little bit of leakage, it's a little dirty, but it gets us by. And Varnish then essentially takes that token now, vets it, and then we'll serve the content as long as it's there. So what have we done? We've essentially said that all of the requests that are valid will come through our API, which means you must have used our player or come to our site or gone to an embed that's vetted by us, we hope. Are there ways around this? Obviously, but for 99% of the fraud, it stops at that point. And here's a little bit of VCL for, I'm not sure why I put this in here. It's not like we're going to stop and digest this line by line, but this is essentially how you do it. It's that simple, right? This is just like take a signature. Yeah, there's nothing secret in there. So maybe it's just impressive, right? There's like, you need to have code in a tech talk, and that's kind of code. It's sad because it's actually configuration. It's like I came up here with like a send file configuration, but all right. So problems, however, moving it to the edge is that you expand the scope of your app. And I'm not sure how much of this will resonate with some of you, but I have this sort of crazy obsession with keeping apps small, portable, and repeatable. I want development and staging and production to be these like little pristine environments where the only difference is a little bit of configuration, which is hopefully managed centrally somewhere. But if you start taking your app's logic, and this is logic, right? This is authorization. And now you stretch it across not only the backend service, but also the front edge cache. Well, now you've created a larger unit that you need to repeat over and over again. And if that unit now includes a service provider like Akamai or Fastly, well, creating development environments or creating staging or test environments has now become a much bigger pain. It's no longer this just like small little thing that you can repeat and drop everywhere. So a downside. I only have a few seconds left, but let me quickly rip through this last problem. And this is geo-restriction. So geo-restriction is pretty simple. We have content. Content's crazy. There's licensing deals involved. There's like partners talking to each other. And a lot of those partners have crazy, well not crazy, but restrictions around, well, nobody west of the Mississippi should be able to watch this. Okay, how do you do that? Well, again, if all your requests are terminating at a server, if I'm the server and you're coming to me with your HTTP request, and I know your IP and I know the rules of the content, this is drop dead simple. I'll take the IP, I'll geolocate it, I'll mash it up against the rules, and I'll tell you yes or no. But what if, so that's geo-blocking. We can envision it as sort of like middleware above our service, like something that soaks up those requests and deals with it. Again, what if we want to cache that though? We obviously don't want to have every single video request hitting us on the back end. Anything would essentially die under that load. So we need to swap the two. We need to put the geo-blocking in front of the cache. And some CDNs out there can help you with this. Like you can work with Fastly or you can work with Amazon, and they have some light support. But for some reason, we allow producers to geo-block at the zip code level for many different countries. And that's problematic because that's not well supported. So what we decided to do instead was, again, to rely on Varnish and its crazy capabilities to help us. So what happens? The API actually generates a geo-blocked configuration. And this is a crazy mashup of sort of like all of the events that need to be geo-blocked and all of the allowed or disallowed IPs. And so it's in this giant JSON struct. The Varnish then sort of loads all this into a shared memory space via this small program. And then there's this Varnish plugin that will refer to this memory map when it needs to map, when it realizes that a request is geo-blocked, it needs to be vetted. It's as crazy as it sounds, but it works and it's pretty fast. So a request comes in, give me the details of an event, and Varnish will then say, hey, let me go check my crazy map and see if you're cool. And if it doesn't show up, well, that's great, everything's fine. Or if it does show up, well, is your IP allowed? And if everything's good, it'll go through. If it's not okay, it'll actually rewrite the request and append a little format to it, which then gives the API a chance to decide what it's going to respond with. In that case, the .geoblocked comes back and we say, is that a 503? Is it a 404? We actually get to modify that. So problems, memory pressure is the obvious one. What happens if you have 1 million events that you're trying to geo-block? How can that memory map all fit on a single Varnish box? Aren't you squeezing out space that you would use to cache pages or API responses? Yes, 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 absolutely. It's not going to work forever. And an IP2 location isn't foolproof. It's pretty easy to defeat this. For example, it's completely unreliable when it comes to mobile. And for mobile, we've had to cook up a separate solution. So again, there's a lot of other problems I could talk about, but I don't have time. So I'm sorry, I'm going to move on. And to wrap up, what I hope you've seen is that these are all real problems that we face with video, from actually distributing video and dealing with the stampede of connections to dealing with the content itself and how to authorize it or how to manage its distribution. But the problems have almost nothing to do with codecs or protocols or qualities or bit rates. It's almost purely just your ability to wrangle HTTP, your ability to build a scalable API, your ability to cache, understand expiry. It's all the same stuff that I think most of us do every day. And that's sort of comforting. It was at least comforting to me when I realized that 8 months into the gig. So thanks so much. I appreciate the time. And I like everybody here. We are always hiring. Thanks again.
Dave, thank you very much. So we got a couple minutes for Q&A.
Oh, jeez. Okay.
Oh, we also have our cool little Jambox thing. So if you have a question, you get to use this deal. Question for you, for me, as far as compression goes, how much of video compression happens, maybe it's a naive question, but happens at the server level versus at the client level?
The vast majority, it happens at the client. If it wasn't compressed, the amount of bandwidth required would be astronomical. I can't remember the numbers, but straight up H.264 compression takes something that would be enormous and makes it astronomically smaller. Like, I don't know how many of you may download video files on occasion through means, but some of those files, like a Blu-ray rip, is huge. I don't know if you've ever seen a raw Blu-ray rip, but you're talking easily over 100 gigabytes. Now, that file, though, if you think about it, is just 1080p, right, at a certain bit rate. And H.264 then is taking that and making it something that can actually stream over a 10 megabit per second internet connection. So the savings is astronomical. And if it wasn't for those compression schemes, there'd be no modern video on the internet.
Interesting. And then how about as far as the compression protocols, have there been any major innovations in the past let's call it 2 or 3 years, or are we still working from things that were created a decade ago?
Yeah, so I'm going to speak a little bit more from the fringes of my knowledge, but I'm starting to crack into this more. But H.264 is quite old, but it's the standard that we use across the internet today. There are advances on the horizon. The problem is getting wide adoption for them. So there are codecs out there like VP8 and VP9 and HEVC and AV1 coming out next year. And these are all advances on H.264. They all get smaller and tighter, and they all look better. The problem is that not everybody out there supports them as widely as H.264. So as the producer, what's my incentive to encode it with a different codec if it's really only playable on a tiny fraction of the people out there? H.264 is just everyone will play it back. Now that landscape is changing. I think Google's doing a great job of pushing the envelope. Surprisingly, Apple is the one really dragging their feet and keeping the industry back. But we expect that to change.
And how do you center stuff vertically in CSS?
God, you know, yeah, that's my last foray, yeah.
Other questions?
Getting off easy. All right.
All right.
Thank you.
Well, we got the crash course. Thank you so much, Dave. That was awesome.